Assalamualaikum guys and good afternoon. Okay, so we continue with uh, chapter 5, our chapter 5, right? Part 2. So in this chapter, we already cover this one, right? So we already cover maximum average power. So actually, our objective here is today is to cover on apparent power and power factor. And then if we got more times, we can go to the complex power and power factor correction, these two. But before we go here, okay, so some revision on effective or RMS value. I will not go deep here because this is already covered in EC1. And then we just go through the formula of effective and effective and RMS value. Okay, all right. So effective or RMS value. So we know that, right? RMS value is stand for root mean squared value. So therefore, this is let's say you have a circuit with a resistor. So this is uh, the power for the resistor, total power dissipated by the resistor is given by this formula, right? So actually by this formula, okay. And then mm, uh, right, so by do some elaboration, so you can see that power actually equal to I squared IRMS squared times R. Okay, so therefore we don't have a RMS value for the power. We only have RMS value for the voltage and also the current, guys, right? So therefore IRMS over here, okay, can be calculated using this formula: 1 over T integration of I squared dt, square root, right? Or square root of 1 over T integration of I squared dt. So that's the formula that we use in order to calculate the RMS value. R mean the roots over here, right? So means means actually the average, right? Of the average value of the current or the voltage, okay. And then squares referring to this one. So this is actually the formula for RMS value, or some book they're using effective. So effective value and our RMS value is the same thing. All right. All right. So therefore, I will not go over here. Okay, just some revision. So I square RMS is also, this is actually not I squared. IRMS is also equal to IM divided by Z2. So therefore, I am equal to, we can say that I am equal to I RMS times Z2. Okay, so this is actually also basic in converting peak value to the RMS value. Okay, all right, so we not go to the example. Okay, and then we go straight away to the apparent power and power factor. So what is apparent power? So apparent power is denoted by a formula by the S, capital S over here. So what is apparent power? Apparent power is the product of voltage and current, right? If and only if the phase angle difference between current and voltage are ignored. So that's mean apparent power is actually P equal to VI, right? So by ignoring the phase angles of the voltage and also the current, that is actually apparent power. So the total power in AC circuit, both dissipated and absorbed, return. So the combination of reactive power and true power. So we can say that apparent power is actually also a combination of reactive power and true power. So when we say reactive power, usually power uh, at the non-linear or non-linear element, which is either power at your inductor and also your capacitor. And when we say true power is actually power absorbed or dissipated by your resistor. Okay, so in AC circuit, apparent power is the product of the RMS voltage and also the RMS current. So when we're talking about the AC circuit, so usually S is actually equal to VRMS time IRMS, right? So uh, yeah, so we can say that apparent power is actually a power, okay, but by ignoring the uh, phase angle difference between the current and also the voltage, right? Okay, so apparent power S is the product of the RMS value of voltage and current. Okay, so this is the another definition. So we can say that apparent power is the product of RMS value of voltage and also current, right? So it is measured in volt ampere because from the formula we know that V times I, so therefore the unit for the apparent power is not watt, guys, so it's volt ampere. Okay, to distinguish it from the average or real power which is measured in watt, right? So therefore this is the reason why we use volt ampere, because we want to distinguish between real power and also apparent power, right? So therefore this is our real power P. Okay, so the formula for real power P is given by Vrms I RMS cos theta V minus theta I, right? So from the definition, we know that the product of Vrms and IRMS is equal to the apparent power S, and then cos theta V and theta I is actually is a power factor, right? So therefore, we also can write the real power in a form of P equal to S cos theta V minus theta I, alright? So power factor, what is then cos theta V and theta I is the power factor. So what is the power factor? Power factor is the cosine of the phase difference between the voltage and the current. It is also the cosine of the angle of the load impedance. Okay, so later on when we go further, so you can see what is actually the power factor. So this is the definition, the direct definition, but later on we can see what is the function of power factor and what is power factor is, right? Okay, so apparent power and power factor. So if let's say uh, we are considering the circuit is purely resistive or having a purely resistive load. So when we say purely resistive load, that's mean the load is consists only the resistor. So we know that uh, resistor is the voltage and the current in a same pace. So therefore when the voltage and the current in a same pace, therefore you got theta V minus theta I will always equal to 0, right? So we know that power factor is equal to cos theta V minus theta I, right? When you got this part is 0, that's mean cos 0 equal to 1. So usually when you have a purely resistive load, power factor is always equal to 1, right? So that's mean when our that's mean our uh, 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 that's mean the power is all consumed by the resistor, okay, because the power factor is 1. Okay, so next when you have a purely reactive load, so that's mean either the load is consist of only inductor or only capacitor. So we know that in inductor and capacitor, the difference between the different angle volt the difference between voltage and current is either lagging or leading, okay, because we are talking about both resistor, inductor and also capacitor. So and then the phase angle between these voltage and current is always 90 degree. So therefore, okay, power factor for this theta v a cos uh, plus minus 90 degree will always equal to 0, right? So therefore we can say that if your load is purely reactive, that's mean purely L or purely C, there's no combination with the R, right? So therefore power factor will be 0. So when power factor will be 0, we can say that the power actually the real power will become 0 over here. Real power becomes 0. So that's mean there is no real power consumption, right? So that's mean if you have a over here either is L, sorry, uh, okay, let's say the load is either L, right? So therefore we can say that power over here is equal to 0 due to power factor is 0. All right, so we can say that this inductor is not consume the power from the supply, right? And then last one, if the load is resistive and reactive load, so that's mean when we say inductor in resistive and reactive load, so that's mean, all right, so let's say you have a supply over here. This is uh, the load will be consist of resistor and inductor, or the load will be consist of the resistor and also the capacitor. All right, RC or RXC or RXL. All right, so therefore we know that theta v and theta I, the value of theta v and theta I will be either larger than 0 or less than 0. So therefore, when theta v minus theta I is larger than 0, we know that the load is actually inductive load. And then when your theta v minus theta I is less than 0, that's mean we know that the load is actually capacitive load. So that means if you got negative value, okay, for theta, so we know that the load is actually consists of resistor and capacitor. And then if you got positive value when theta v minus theta I, so we know that our load is actually consists of in when we say inductive loads, that means resistor and also inductor. So always remember this, when we have inductive loads, so that's mean we can say that the load is lagging. And then when you have a capacitive load, that's mean the load is leading. That's mean is leading. So we can say that inductive loads usually V, for inductive load, so usually V leads I, right? So that's why you got when V leads I, so this is larger, mine's lower, so you still got the value is bigger than 0, right? And then when you have inductive load, right, so inductive load usually, right, so the I will lead uh, the voltage, right? So therefore you got negative value over here, so this is in a capacitive load, sorry, this is capacitive, sorry, right? Okay, so next we go to the power factor. So from the formula that we see here, the real formula over here, you see we have a power factor, which is power factor is cos theta v minus theta I. So therefore what is actually power factor? So with some introduction, most plant load inductive and require magnetic field to operate motor, transformer, fluorescent lighting. So the magnetic field is necessary but produce no useful work. So the utility must supply the power to produce the magnetic field and the power to produce the useful works. So you pay for all of it. So these two type of current are the active and reactive component. Okay, so actually what they want to say here is actually before we go to the power factor, okay, you can they said that most plants loads are inductive, right? So because of what, usually in order to do works uh, with a bigger machine, so usually you need a motor, you need a transformer, right? So especially in the plant, so you need a transformer. So we know that transformer is like a conductor, what it's like a coil, or it's like a more to inductive behavior, right? So therefore uh, uh, in order to the supply that we use is only not to activate uh, uh, not to activate uh, the real load, but also at the same time you need to activate the motor and the transformer, right? Even though we are not use the motor and transformer directly, but this motor and transformer is necessary, all right, because uh, is needed, okay, in order to produce the useful work, right? So that's mean uh, to produce a, a power, so you need to use a transformer and motor, so in order to make sure uh, uh, we can produce a high volume of the power that we need, or that we use to produce a useful works lah. So therefore power factor is very important, so especially in a power plant system or in industry and so on. Usually is involve a bigger power plant or a bigger system, right? So the power factor is a very important quantity. Its importance stem in part of the economic impact it has on industrial user of large amount of power. So we know that in a large industrial, we use lots of we use a large amount of power, or we use a lot of energy. All right, so let's say in a factory, so uh, in order to produce a product, all right, so you need a bigger machine. That bigger machine usually they need bigger power, so therefore they use transformer, they use a motor in order to operate the bigger machine, right? So therefore uh, we can say that this machine is actually needed, okay, in order to produce a product, right? Or to produce a high power for the bigger machine, something like that, okay. So a power factor, we can say that uh, a power factor of 1 or unity power factor is the goal of any electrical utility company. Okay. Uh, so that's mean um, if possible, okay. So let's say in order to get a power factor equal to 1, okay, so that's mean uh, if possible, so the theta v and theta I must be equal to 0. So that's mean there's no lagging and leading load uh, to the uh, to the system, okay. But reality, we cannot do that. Reality, we know that, like I said, in order to produce a useful work, you need to use a motor, transformer and so on. So motor and transformer usually they are inductive, more to inductive capacitive, right? Inductive loads, right? So therefore in order to get the power factor equal to 1, is quite difficult, but we can reduce the inductive effect of the load, okay, by introduce the capacitive load. All right, so later on we can see. So actually what you need to know here, is power factor. The best power factor is actually equal to 1, but reality we cannot achieve equal to 1, because it is impossible, because the load, we cannot have a resistive load all the time. So usually you have a uh, um, inductive load or capacitive load, right? So therefore we need to do some adjustment in order for us to get a power factor nearly 1. Okay, so we can say that our goal is actually to get a power factor equal to 1, or unity power factor. Power factor less than 1 need to supply more current to the user for a given amount of power use, right? So why we want 1? Because when the power factor is less than 1, so we need to supply more current, right? So, however, they incur more line losses. They also must have larger capacity equipment in place. As a result, an industrial facility will be charged a penalty if its power factor is much different from 1, right? So, uh, because when the power factor is less than 0, so is use uh, large power, but the power is not a real power, right? So we know that power that absorbed by the uh, reactive load is not useful power. Okay, the real power is actually power absorbed by the resistor. Okay, so industrial facility tend to have a lagging power factor, like I said. So that's mean current lags voltage. Uh, this is primarily the result of having a lot of electrical induction motor. The winding of motor act as inductor, as seen by the power supply. So therefore, capacitor have the opposite effect and can compensate for the inductive motor winding. Some industrial sites will have large bank of capacitor strictly for the purpose of correcting the power factor back towards ones to save the utility company charge, right? So therefore, in order to balance uh, the power, uh, uh, we use, like I said, we use a capacitor uh, to ensure that our power factor is can be nearly to 1, right? So power factor is very important due to the low power factor will incur a lot of power, so therefore your bill will be higher. Okay, so okay, let's say uh, uh, okay, this is the analogy of power triangle. Okay, so okay, so this is let's say you have a aeroplane travel from destination A to the destination B, right? Okay, so um, we can say that we know that aeroplane is not a land vehicle, is a air transportation, right? So therefore, in order to go to the point A and to B, so the aeroplane itself need to move uh, upwards, right? So therefore, we can say that in order to take off, right? So to the we you need a fuel to maintain the altitude of the aeroplane. So therefore, we can say that this is similar with the reactive power, all right? And then the real part is actually we want our aeroplane from point A to point B. right? So so the fuel to get from point A to point B is actually the active power. This was the real destination that we want, right? But uh, uh, of course, when you are using an aeroplane, so uh, you need to involve this reactive power, or the tech uh, uh, the is I mean, it's actually the aeroplane still need a fuel in order to take off, but the total you pay for the fuel is actually include the vertical portion of the flight as well as the fuel of the horizontal portion of the flight. Hopefully you can understand me, right? So let's say if you another vehicle that is uh, a land transportation, in order to get to point A, to destination A to point A to B. Okay, so you just straight away, right? So the fuel that we consume is actually from point A then point B. But when you use a air transportation, all right, so uh, the fuel is needed in order to maintain the latitude altitude of the aeroplane. So therefore we can say that we still need to pay uh, all here, all right, the total from the vertical and horizontal portion of the flight. Okay, so this is the analogy between the real power, this is the reactive power, and then this is the apparent power. Okay, this is apparent power. So similar with the bill, right? So the utility bill, so like I say, if the load uh, we know that the real power uh, is actually, if you have a resistive load over here, right? P due to the resistive load, but we know that our loads can usually cannot only consist of resistive, is must involve inductor and capacitor. So inductor and capacitor is actually your reactive part. So therefore the apparent power, for the bill, utility bill, you still need to pay for both the reactive and also uh, uh, resistor, due to the reactive and also resistive load. Okay, so this is what the analogy of the power triangle. Okay, so this is another analogy. So you can say that if you buy if you want to buy buy a cappuccino, right? So usually cappuccino consists of the froth over here. Froth is actually uh, milk bubbles, right? So and the coffee over here, right? So you the amount that you pay is actually for the whole cup, right? So therefore, but what we enjoy most is actually, what you can enjoy is only the coffee over here. So this is the froth. So usually it's just bubbles, right? So usually we can say that the real thing that we enjoy is actually this part, coffee, and then the reactive power is actually uh, the bubble part. Okay, so you don't need it, but uh, you must have it. Or if you don't have a froth up there, so it's not called cappuccino, it's only called a coffee, right guys? So therefore mm the overall over here is similar with the apparent power, or the whole cappuccino you pay is actually similar with the apparent power. Okay, so the power triangle, similarly, motor require reactive power to set up the magnetic field, while the active power produce the useful work, shaft horsepower. So the total power is the vector sum of the two and represent what you pay for. So from the analogy over here, so usually in order to analyze the power, okay, so it is better for us to have a power triangle. Okay, so this is a power triangle. So usually this part is the active power, and then unit in kilowatt. When we say active power, this is the power that we need to produce the useful work. And then this part is actually the reactive power. Reactive power, the unit is kilowatt ampere reactive. This part usually is useful to set up the magnetic field. And then S over here is actually the total power, and then the unit is kilovolt ampere. This is what you need to pay off. So this is the relation between uh, active power, reactive power, and also total power, right? So all this relation can be put in a triangle, and then we call it as the power triangle. Okay, power factor is the ratio of active power to total power. So we know that PF is equal to um, active power is P, total power is S. So this is our power factor. And then power factor um, also equal to cos theta, right? So we can say that power factor is a measure of efficiency from output, the ratio between output and input. Or power factor is also the ratio between real power and also apparent power. Right. So this is where we put a power triangle in a form of mm, in uh, 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 in a form of we call it a complex uh, in a what complex uh, a real part and also imaginary part. Okay, if you plot it in a x-axis and y-axis, this is what we get. So usually a real power, all right, is will represent with by the real axis, and then your Q over here is represented by the imaginary axis, and then the vector S over here is actually the apparent power. So we can say that P, real power, is equal to magnitude of apparent power cos theta, and then apparent power is given by V and I over here, right? So the power factor, that part of the apparent power that is related to the mean energy flow. So you can find also cos theta, right? Cos theta from this formula, right? From this formula we can say that cos theta is actually P divided by modulus S. And also we know that S over here by using uh, theorem Pythagoras, so you can say that this part is actually square root of P squared plus Q squared, right? And then cos theta is given by cos theta is actually cos uh, cos is P uh, cos is P divided by uh, S, right? So similar with this. Or you can also say that tangent, inverse tangent Q divided by